Confusion matrix explained visually, thresholds and errors. In this video, we'll take the confusion matrix from a static table and turn it into a visual story. We'll look at a model that predicts whether visitors on an e-commerce website will make a purchase. Each customer gets a score, and by choosing a threshold, we turn that score into a prediction, purchase, or no purchase. Then we'll see exactly where the four parts of the confusion matrix come from: true negatives, false positives, false negatives, and true positives. By the end, the confusion matrix won't just be a table of numbers. It will show how a model makes decisions, where it makes mistakes, and how those mistakes change when the threshold moves. Let's start with the business case. Picture a big sale day at an online store. Some visitors are just browsing, some are close to buying, and from the outside, those sessions can look surprisingly similar. The model looks at clues from each visit, searches, product views, carts, exits, and patterns from past shoppers. From those clues, it gives a purchase score. But a score is not a decision. It is just the model ranking which visits look more likely. The decision happens when we choose a threshold. Above the line, predict purchase. Below it, predict no purchase. Then the useful question is not only, was the model right? It is, what kind of wrong did it make? A false alarm wastes effort on someone who is not going to buy. A missed buyer means we overlooked someone who actually did. This lesson shows how a confusion matrix keeps those cases separate. The first thing we need is the answer key. Each dot is one visit to the store. When the colors appear, they are not the model's guesses, they are the real outcomes. Purple visits purchased and teal visits did not. Every error we count later comes from comparing the model's prediction back to these truth labels. Next, the model gives every visit a score. Think of the score as a ranking. Visits that look more like past buyers move to the right, and visits that look less likely move to the left. This is useful, but it is not a final class label yet. A score tells us how strongly the model leans. It does not tell us what action to take until we choose a cutoff. If the score were perfect, all the buyers would sit cleanly on the high score side and all the non-buyers on the low score side. Real behavior is noisier. Some people look unlikely and still buy, some look promising and leave. Those mixed regions are where any single cutoff will struggle. The confusion matrix will count the mistakes, but the reason for the mistake starts here, in the overlap. A score becomes useful when we decide what action it triggers. Here, the positive class is purchase, and the threshold draws the line. Scores below the line become predicted no purchase. Scores at or above it become predicted purchase. That cutoff is not automatically given by the chart. It is a choice about how cautious or aggressive we want the classifier to be. Now the trade-off becomes visible. Lowering the threshold is like casting a wider net. In a store, that might mean sending more reminders or offers. You catch more real buyers, but you also spend attention on people who were not going to buy. Raising the threshold is more selective. It reduces false alarms, but some real buyers fall below the line. There is no free threshold. The right cutoff depends on which mistake hurts more. Quick pause. This threshold is easiest to understand when you can move it yourself. The interactive web version is linked in the description. After the video, drag the line and watch the matrix change. If this kind of visual lesson helps, hit like and subscribe. And now, let's build the full matrix. After the threshold is applied, every dot has two identities. Its color still tells us the truth, purchase, or no purchase. Its lower position tells us the model's prediction. That distinction matters. These lower packs are not new data and not a second sample. They are the same visits sorted into predicted no purchase and predicted purchase. The four outcome names are easier if you read them as two questions. First, did the prediction match the truth? If yes, it is true. If no, it is false. Second, did the model predict the positive class, purchase? If yes, it is positive. If not, it is negative. Put those together and the vocabulary stops being random. True negative, false positive, false negative, true positive. The confusion matrix is not a new calculation. It is a table that organizes the four combinations. Read the axes first because different tools sometimes flip them. In this lesson, rows are actual outcomes and columns are predicted outcomes. The diagonal cells are correct decisions. The off-diagonal cells are the two mistakes we care about. This is the part that many students miss. A confusion matrix is tied to a threshold. The truth labels do not change when the line moves, but the predicted labels can. So the same score model can produce different matrices. When dots cross from one prediction column to the other, the counts update because the decision rule changed, not because the customers changed. One matrix shows one cutoff. That is useful, but it is only a snapshot. To understand the model's behavior across the whole range, we can sweep through many thresholds and recompute the same 4 counts each time. The curve view is that sweep turned into a chart. The curves do not choose the threshold for us, they show the consequences. As the cutoff rises, predicted purchases usually shrink. That can reduce false alarms, but it can also turn real buyers into missed buyers. As the cutoff falls, we catch more buyers, but we may call too many sessions purchases. The chart is a reminder that model evaluation is not only about accuracy, it is about choosing an error profile that fits the problem. Before we wrap up, read the spinal frame like a checklist. At the top, the model is still a ranking machine, each session has a score, and the threshold turns that score into a prediction. The matrix below crosses that prediction with the truth. The names come from 2 questions. Did the prediction match reality? That gives true or false. Did the model predict the positive class? Purchase. That gives positive or negative. So a false positive is a false alarm, predicted purchase, but no purchase happened. A false negative is a missed buyer, predicted no purchase, but the customer did buy. The chart on the right reminds us that the matrix is tied to the threshold. Move the threshold and the counts move with it. Lower thresholds cast a wider net, higher thresholds are more selective, neither is automatically better. The matrix below crosses but no purchase happened. The right threshold depends on the problem. So when you read a confusion matrix, ask 3 questions. What is the positive class? What threshold created these predictions? And which mistake costs more here? The interactive version of this widget is linked in the description. Try moving the threshold and watch the matrix and curves respond. If this helped confusion matrices, click like the video and subscribe for more visual machine learning lessons.